Okay, so welcome to the second meeting. So the plan for this meeting is for me to do an example review, an example presentation, and hopefully we'll have a discussion at the end. And if there's time, I'll do another one as a bonus. Let's see. Because there may be some reflections that we do while we do the review. We may not have enough time for both. Technically, we should have enough time for both, but let's see. Sometimes I like telling stories, so once that happens, I think we're not going to be done with the first one. Okay, so if you remember this slide from last time, this is the suggested paper presentation and discussion format that I have, and I'm going to follow this pretty much exactly. I would like people to give 25 minutes or so summaries. I cannot guarantee my summary will be that long. It may be a bit longer if I start telling stories, but you can tell me to stop if the stories are not interesting. Hopefully they will be interesting. But I'll try to keep the stories to the end. I would like about a 10-minute critique plus 10-minute discussion. So of course less structured. Hopefully there will be brainstorming and discussion in the end. Does that sound good? Okay. And before I start, we got your preferences. We will have 11 sessions of presentations, right, Mohammed? Okay, that's good. And there will be 2 presentations in each of the 11 sessions. Is that also correct? Okay. Basically, hopefully we'll have at least a 10-minute break in between, so which means that there's maximum 50 minutes total for each presentation plus discussion. That's what we should really strive for. And we will probably take the entire 2 hours in each meeting given this, right? In each presentation, as you know, one student presents one paper and leads the discussion. I already discussed this, so I'm not going to talk about this. I would strongly recommend following the suggested guidelines. Remember the picture by Salvador Dali earlier? It's better to learn the fundamental principles first before you start consciously breaking them, right? Hopefully the goal is you'll start breaking them. If you start breaking them right away, I'm not suggesting that you will do a bad job, but the likelihood that it may not go well is higher compared to the likelihood of following the guidelines, at least in my experience. But there's nothing that prevents you from breaking them also. Okay? You may do a great job if you break them too, I don't know. But it remains to be seen. Okay, so this is the algorithm for presentation preparation. A more succinct way of putting it. Basically, please study lecture 1, especially if you weren't here. Read and analyze your paper thoroughly. Discuss with anyone you wish. Use any resources. There is no limitation. Absolutely, it's all very good. Prepare a draft presentation based on guidelines. And then, this is mandatory, meet your mentors and get feedback. Revise the presentation and the delivery according to the feedback. Meet your mentors again and get further feedback. And again, revise the presentation and delivery. So it's a very simple algorithm, right? So I like thinking of a lot of things in the world like algorithms. Like when you're writing a paper, you're also following an algorithm, in my perspective. And as long as you stick to an algorithm, you can write very strong papers because you can refine the algorithm over time. Okay, I think meetings are mandatory. I think we already said this. You have to schedule them with your assigned mentors, and hopefully you will benefit from it. In the past, the feedback has been, this is a great part of the course, basically. I don't know, not everybody has to agree, of course, but most of the feedback has been very positive in terms of working with the mentors. And this is very important. Practicing is really important. I remember, even after my PhD, the talks I gave, the first talk I gave, not the first talk, but maybe even the third talk I gave after my PhD, I practiced a lot. This was a conference talk, and I practiced in front of a mirror. I like practicing in front of a mirror because I can see myself also, and you can be conscious of what you do while you're presenting if you're in front of a mirror. And I think when you're giving your first talks or so, I always recommend scripting your talk. Like in the part, if you're using PowerPoint, in the part where you have comments, it's good to have a script of the talk so that you know what you're going to say. And especially if you're doing these presentations early on, I used to write the script completely. In fact, if you download, for example, the PAR-BS presentation, Parallel Batch Scheduling presentation from my website, you will see the exact script. with all the annotations. You'll see the boldface points. You will see how I try to boldface the connecting parts between the slides. And following that script is very, very useful in improving your presentation skills. Later on, of course, if you're given hundreds of presentations, you may not need to follow that script. But initially, to get you started, that script is extremely important, I think. I benefited a lot from it. And I think my students have benefited a lot from that also. So I would suggest that. Actually, PowerBS is one of the presentations that are planned for today, but I don't think we're going to get to it because there are 3 presentations planned for today, and PowerBS is the 3rd one. But you can take a look at the slides and the script over there. So scripting and practicing is very important, I think. Okay, so basically we're going to do example paper presentations because I think learning by example is a great way of learning. You can only learn so much in the world, I think. If you had to learn everything by doing, it's going to take a lot of time. I think learning by example is a great way of learning from somebody else's experience. That way you can leap ahead, if you will, because you don't need to do that thing. Especially if you're a good learner, by example, I think by reading a paper, for example, you can learn how to write a good paper. I enjoy doing that. So we will do at least one today. And essentially we're going to follow the structure. I don't know if I want to go through this, but maybe I'll go through this. Basically, you'll see these slides: background, problem and goal, novelty, key approach and ideas, mechanisms in some detail. Not necessarily in this order, I think. Key results, methodology and evaluation, summary. Basically, that part constitutes the summary of the paper. About 25 minutes or so when we get to the summary. And then we'll talk about strengths, weaknesses. Remember, you're going to be very critical here. Thoughts and ideas. And I'll try to involve you also in the discussion, hopefully. And takeaways, and open discussion and brainstorming. Does that sound good? Okay. So we're going to do one paper. Has anyone read this paper before? No? Okay, some people have. Only one person has. Nobody else? Okay, that's good. That means that this is going to be fresh for you. Although hopefully this is not going to be the common case in future presentations because you will know the paper schedule. And I would recommend at least skimming through these papers. So I'm going to present one of my own papers. I'm going to kind of cheat. You will not have this luxury, I think. How many of you have written papers? Scientific papers? Okay, no. So you will definitely not have this luxury in the course. In the future, you may have this luxury, of course, but maybe not in the same way. But of course, I'll give you hindsight also because I know the area quite well in this case. Okay, so we're going to talk about this. And I'm going to use some of the slides that my student has used, not all of them. This was work done by Vivek Seshadri, my PhD student. It was part of his PhD thesis. This is not his first paper. His first paper was on caching, published in PAC 2012. But based on discussions with me, he actually did his PhD on a much more forward-looking topic as opposed to caching. His caching papers were great actually also, but I'm not going to talk about those. He has actually 2 papers that are not part of his thesis. One is the caching paper, evicted address filter, and the other is about caching and prefetching, integrated caching and prefetching. But later he focused on more in-memory processing, in-memory operations, and this is one of the first papers. Okay, so I'm going to describe this paper. So you can see that the authors are there, the conference is there. It's good to have a slide that looks like this, that sets the stage. And this is work done by us collaboratively with Intel folks in Pittsburgh. So let's start with the background, problem, and goal. Essentially, the problem is memory channel is a bottleneck in modern systems. You can see that it's a bandwidth limited channel, and it's a long latency channel, and it's also a high energy channel. And the goal is to reduce the memory bandwidth demand in workloads. And we would like to reduce the unnecessary data movement. And there are 2 cases where unnecessary data movement is very prevalent in existing systems. Whenever you're doing bulk data copy and bulk data initialization. What does that mean? You're copying a large page to another page, for example. That's one example. Or whenever you're copying a small page to another small page, or a small item to another small item, you're still moving data. And bulk data initialization, let's assume that you're initializing a page to all zeros. You need to write all zeros to a page. Now this becomes even worse if your pages are large, right? 1 gigabyte, let's say. Now you need to do a lot of data movement, a lot of writing into the memory. So, and there is a lot of work that talks about this bulk data copy being a limiter in terms of system performance, especially operating system performance. These are some interesting papers. You can see the titles, right? Why aren't operating systems getting faster, as fast as hardware? Maybe hardware is lacking support for these operating system operations. And there's some work actually looks at hardware support for bulk data movement and copying. These are discussed in the paper, but I'm not going to talk about that. We can talk about them in discussion maybe later on. So these are important things in real applications. Whenever you fork a process, for example, you do copy on write. You copy your pages to the other process, but you don't necessarily do it right away. You basically make the page, for example, copy on write enabled, and whenever the child process or the parent process writes to the page, at that time you initiate a copy, right? This tries to minimize the copies clearly for read-only pages, for example. You don't need to do the copies. But there are enough pages where you write. As a result, page copies are a lot. Zero initialization, actually all of the operating systems that I know of, whenever they deallocate memory, they initialize the memory that they deallocated to all zeros so that information is not leaked from that memory from one process to another process. You could also initialize it for something else. Checkpointing, virtual machine cloning and deduplication, those are actually interesting. Page migration. We may have a story later on, if you remind me, on this virtual machine cloning. And there are many more applications. And this is actually in hindsight. This is not in the paper clearly because this paper was published 2 years after the paper that I'm describing is published. Google showed that in all of their data center workloads, more than, approximately 5% of the cycles is spent on just two system calls, memmove and memcopy. This is not all of the copies in the system. This is just two system calls that are doing copying and initialization, as you can see. And that's also an interesting paper. That's part of the reading list. If you've chosen that, that may get discussed. Okay. And actually, just again, I'm getting ahead of myself, but this paper cites this RowClone paper that I'm discussing as a potential solution to reduce the data movement in systems. Okay, so let's take a look at how this data movement, how the bulk copy initialization is done in today's systems. I'm going to focus on bulk data copy. Let's say that we're copying the source page to this destination page. What do we do in today's systems? Basically, we need to go through the processor. We bring the source page byte by byte all the way into the L1 cache using load instructions. And then we bring the destination page byte by byte. We do the copy, a store basically, byte by byte. And then write the destination page back into memory whenever the data gets flushed from the caches. Clearly this is high latency because you do a lot of communication between the memory and the CPU. High bandwidth utilization. We were basically transferring 4 kilobytes here, and you're doing a write back 4 kilobytes, right? That's 12 kilobytes of data transfer. If your pages are large, now it becomes even bigger. This causes cache pollution because you may not actually need this page immediately, right? And then you're evicting stuff from the caches. But in today's systems, you can actually solve that problem by offloading the copy to the memory controller by setting up the direct memory access engine. There are ways you can set up this copy to be done just through the memory controller without disturbing the caches. That requires some more overhead also. But that's really the state of the art, doing this copy through the memory controller. And it causes a lot of unwanted data movement because if you're not going to use any of this anytime soon, you're bringing all of this to the caches, right? Which is not necessary. In fact, you may never use some of this. You may, for example, be initializing a huge chunk of memory. Let's take the terabyte of memory. You're writing all zeros to it. It's not a form of copy, but it's really a form of initialization. Then you're actually moving a lot of zeros over the memory bus, right? Okay, so let's go back to the case of copy, 4 kilobyte page copy from here to here. If you do it in the best mechanisms that we know of today through the direct memory access engine without going through the hierarchy over here, the paper shows that in some technology assumptions, in DDR3, it takes about 1046 nanoseconds and 3.6 microjoules. Okay, that's the problem basically. Now, what does the paper propose? Basically, this is novelty, key approach, and ideas kind of together. So the paper argues for a solution that looks like this. As opposed to going through the processor, the paper enables the memory to do this copy within itself. And that's the idea. It's called RowClone. And let's take a look at the benefits first. The paper shows a way of doing this at low latency because you're not moving a lot of data through these interconnects, through the hierarchy. Low bandwidth utilization because you're not moving data at all. In fact, it's zero data bus bandwidth utilization. You only transfer the data that you need later on. No cache pollution in the caches, but you could eliminate that today anyway with the direct memory access mechanism. And no unwanted data moment. Again, you'll only bring the data that you need later on. And the paper provides a mechanism that reduces the 1046 nanoseconds to 90 nanoseconds and 3.6 microjoules to 0.04 microjoules. And let's take a look at the key idea, at least one of the key ideas in this paper that provides the highest benefits. And now we're going into a little bit more detail, right? We gave the high level, now let's look at how it's implemented in the low level. In the low level, if you look at a DRAM subarray, it consists of two-dimensional array of cells. In this case, let's say 4 kilobytes over here. It's nicely aligned to a 4 kilobyte page. Keep that in mind. That's going to be one of the potential shortcomings later on. Now, the idea of the paper is very simple. If you want to, the paper, if your source page is somewhere in the subarray and the destination page is also somewhere in the subarray, you can copy data from the source page to the destination page by doing two consecutive activates. The first step is to activate the source row, which brings the data into the sense amplifiers. Now the data is strong in the sense amplifiers, it's amplified. Now the second step is to activate the destination row, which implicitly deactivates the source row, but the data is still stored in the sense amplifiers. Once you activate the destination row, the sense amplifiers get connected to the destination row, which means that the data that they store is driven into the cells of the destination row. And that's the key idea, basically. By doing these two consecutive activates, you can copy the data from the source row to the destination row by going through the sense amplifiers. Okay? So that's the idea. It's negligible hardware cost. I'm not going to go into the hardware cost over here, but it's actually zero hardware cost almost, and we'll talk about that later on in a little bit. Okay, so let's go into a little bit more detail in terms of the mechanisms. That's the basic mechanism, but it's not the only mechanism. So if you look at a DRAM chip organization, a DRAM chip consists of multiple banks. In each bank you have multiple subarrays, and you have a shared bus over here. Okay, each bank consists of subarrays, and each subarray consists of rows of DRAM cells and the row buffer or sense amplifiers. The RowClone idea proposes three different kinds of copying internally. And we'll talk about initialization also. One is the intra-subarray RowClone, what we just talked about. It's row granularity. This is called the fast parallel mode in the paper. You basically have a fast parallel mode of copying data within a subarray. But you can also copy from one bank to another bank. This is called Interbank RowClone. It's byte granularity. So these are different granularities, as you can see. This is called pipeline serial mode for the reasons that will become clear soon. And there's the inter-subarray, which is the least beneficial part. If you want to copy from one subarray to another subarray in the same bank, there is no direct connection between those subarrays, so you really need to go through some other bank, as we will briefly see. So fast parallel mode, as I already described this, you basically copy the source row to the row buffer first, and then row buffer to the destination row by doing two consecutive activates. I don't know why that didn't show up, but it doesn't show up over here. But that's the destination row. Imagine that writing DST row over there, which is really how the presentation should be, but somehow it didn't show up. Okay, so those are the two steps. Then the key question is, how do you actually do the row buffer to destination row? So let's go into a little bit more detail in the lowest level. So now I'm focusing on a single cell in a single bit line. That's how the first source row looks like. That's the one cell. That's the destination row, one cell. And this is sense amplifier. We're focusing on only those rows. And imagine that you have many, many bit lines that are parallel. So let's say when we activate the source row, assume that the source row is really charged in this case, and initially the sense amplifier is pre-charged, which means that both sides are pre-charged to VDD over 2. When you activate the source row, you connect the access transistor and essentially you connect the capacitor to the bit line, which perturbs the charge little in the sense amplifier, in the bit line, and the sense amplifier detects this charge perturbation, and it basically amplifies it. It amplifies this little difference. That's how the sense amplifier is designed. Now the bit line becomes VDD, this becomes 0, so now you detected that this was VDD, and because of charge sharing principles, now you have VDD over here, it fills the source row, right? That's essentially how charge sharing operates. Now you've detected it's VDD. Okay, that's the first step. Now the second step is activating the destination row, which means that you deactivate the source row. But now sense amplifier is still driving VDD over here. It's already sensed. Once you connect the destination row over here, what happens is because of charge sharing, the sense amplifier essentially fills the destination capacitor. That's how data gets copied into the destination capacitor. I'll give you an example where the source row is charged, destination row is discharged, but you can look at different examples. It works. Okay, so that was the intra subarray. Now we have the destination row. Isn't it nice? Okay, so basically intra subarray looks this way: source row, and somehow something happened here. But basically, we want to try to copy the source row data into the destination row data. You first activate the source row, which goes into the row buffer, and then you activate the destination row, which essentially gets the source row data this way. And essentially, all three look like the source row at the end of the process. All of the data, the same data is all over there. Okay. And the results very quickly in the technology that's examined in the paper, you can reduce 1046 nanoseconds to 9 nanoseconds, and energy, this is DRAM energy. It should be written DRAM energy over there. That's a fault in the presentation. It reduces this copy energy to 3600 nanojoules to 40 nanojoules. No bandwidth consumption, no data bus bandwidth consumption, and very little changes to the DRAM chip. So there are constraints in the fast parallel mode. Clearly, the location of source and destination both should be in the same subarray, right, to be able to do this. Size of the copy is a constraint, meaning you copy all the data from the source row to the destination. What if you want to copy a small fraction of the source row? You cannot support that in the fast parallel mode because of the nature of it, right? Whenever you activate a row, all of the cells in the same row are activated at the same time. There's no way of fixing this problem unless you change the structure of the subarray a little bit. So there's another proposal in the paper that talks about interbank copy, where if the source data and the destination data are in two different banks, how do you do the copying? And it again uses a lot of the structures that are already present in DRAM. So basically it uses the shared internal bus that connects the banks. Let's assume that you want to copy these 3 bytes, let's say, or 3 64 bits, assuming that the shared data internal bus is 64 bits, 3 8 bytes, let's say 24 bytes, from here, from this row in this bank to this row in this bank. The way it's done is memory controller issues commands such that it sets this bank to the read mode, sets this bank to the write mode, and it reads from this bank in a pipeline manner and writes to this bank in a pipeline manner. That's the idea. It orchestrates these requests, and the paper describes how the memory controller does that. Clearly you need to activate this row, and then read from here and write from here. So you need some changes to the memory controller, and you need very slight changes to the DRAM chip so that you can do this at the same time. Okay, that's the idea. So it overlaps the latency of the read and write over here, and as a result it leads to significant latency reduction, not as good as if we did it with the intra subarray, and still significant energy reduction, as you can see. Okay, so the generalized RowClone intra subarray we discussed, interbank we discussed. The hardest part is whenever you have data in this subarray and you want to copy the data to another subarray in the same bank, because there is no connection between these subarrays in existing DRAM chips. This paper proposes to use interbank copy twice. What is the idea? You basically take a row from this subarray, write it to some other bank, and now you have the data copied to some other bank through the second mechanism, interbank copy. And then you take the data that you wrote to some other bank and you write it to this other subarray, destination subarray. Clearly you move a lot of data inside the DRAM chip. And the paper shows that you don't get a lot of benefit in terms of latency, but you get a lot of benefit in terms of energy because you don't move the data outside the DRAM chip. So all of these, the paper claims that there's a 0.01% area cost into the DRAM chip. So it's not a lot of area cost. It's not costly. Okay, so this is in terms of copy. Let's talk about initialization briefly. Initialization is actually a special case of copy. This is one example given in the paper. So one thing you could do is if you're initializing the memory to zeros, for example, you can fix a row to zeros, all zeros, hardwire a row to zeros in a subarray, for example. It's very small loss in capacity, since zero initialization is common in workloads, as we will see. You can do this, and then the next step is basically copy this row, right? You can copy this row using any of the mechanisms that we've discussed. In the same subarray, clearly you can copy it to other rows in the subarray. That way you could initialize an entire subarray to zeros very quickly. 90 nanoseconds times the number of rows that you have in the subarray, right? -1. That's the idea. If you want to initialize something, an entire row to some other value, you initialize the row to that value, write data to it, and then you copy that data to the other subarray. to the other rows in the subarray. That's the idea. So that's why initialization is really a special case of copy. And yeah, basically we've discussed this. Initialization with arbitrary data, you initialize one row, copy the data to other rows. Zero initialization is most common. You reserve a row in each subarray, always zero. You copy data from the reserved row. This is called the using the fast parallel mode. And this leads to 6x lower latency and 41.5x lower DRAM energy in these results with very small loss in capacity. Actually, this resembles the idea of hardwiring a register to zeros, right? Since zero is very common, you hardwire a register to zero in many ISAs. That's essentially what's happening. You hardwire a row to zeros in the subarrays in the DRAM. Okay, so this is a summary of the at least the raw results in terms of copying and zeroing in the paper. Relative latency reduction. Intra-subarray is very significant. Interbank is not terrible. It's almost 2x. Inter-subarray, you don't get latency benefit. And zeroing, you get significant latency reduction. And copy, in terms of energy reduction, you get very significant energy reduction in DRAM energy for intra-subarray. Somewhat less, actually quite less in interbank, but it's still not. It's still quite high. And even inter-subarray copy leads to energy reduction because you're not moving data across the heavy interconnects outside the DRAM. And zeroing energy reduction is about 41x as we discussed. And all this comes at very low cost, 0.01% increase in die area. So next the paper talks about system design to enable RowClone. The RowClone is really a substrate on top of which applications can accelerate copy and initialization operations. But to be able to enable that, you really need to build across the stack. And the paper talks about some of the issues across the stack. How to communicate occurrences of bulk copy and initialization across layers. The paper talks about some ISA instructions. We will briefly talk about that. Some of these already exist. The repeat move S instruction, for example, that we talked about in digital circuits. That's an example that enables you to do the copy. How do you ensure cache coherence? The paper proposed a very basic solution. So if you have some of the data that's already present in the caches, you need to flush the caches to memory first. This is a higher problem in general. We may get to that again in the discussion, potentially. How do you maximize latency and energy savings? Clearly, the picture that the paper shows is very heterogeneous, right? The benefits depend very much on where the source row is and where the destination row is. So if you somehow want to maximize the latency and energy savings, you really want to allocate the source row and the destination row in the same subarray. And the paper proposes that you perhaps the operating systems and the system software should be conscious of the structure of the DRAM such that whenever you're doing a copy, the destination row is in the same subarray. That would be nice. Of course, the paper doesn't go into the design of an operating system or a memory allocator to be able to do that. But if you really want to maximize this, that's what you really want to build. And of course, how to handle data reuse. There's a discussion in the paper which we will briefly talk about. There are some cases, actually the paper shows that you don't want to do this copy always inside memory because there are some cases where data reuse is good. Sometimes you want to bring a lot of the page into the caches after you do the copy. And if you, in that case, if you do the copy inside the memory, you lose performance compared to existing systems. The paper proposed a solution for that. It's a small solution, but it at least recognizes the problem. So let's talk about this very quickly. Basically, hardware-software interface. The paper proposes two instructions, memcopy and meminit, to be added to the instruction set architecture. And similar instructions are present in existing ISAs. x86 has some. PowerPC also has some IBM Power architecture. And microarchitecture needs to support this clearly. And the proposal in the paper is to check if the instructions can be sped up by RowClone with some heuristics. And if so, export the instructions into the memory controller. If not, do the instructions in the processor. Right. Okay, managing cache coherence. RowClone clearly modifies data in memory, so you need to maintain coherence of cache data. So the paper proposes to handle this similar to how the direct memory access based copy is handled today. If you remember direct memory access, the memory controller does the copy. Source and destination are in memory. And essentially the same issue needs to be solved when you're doing a direct memory access. You have some data in the caches, and you're copying a source page to a destination page with the memory controller, so you need to flush the data in the caches first. It may not be the best solution, but the paper doesn't tackle the cache coherence problem further than this. And there are some additional optimizations that could be done. And the paper also proposes maximizing the use of fast parallel mode. As I said, it wants to make the operating system subarray aware. And some primitives that are in the operating system already are amenable to the use of fast parallel mode. Copy on write, for example. you can allocate the destination the same subarray as the source, because whenever you're doing a copy on write, you realize that you need to allocate a destination page at this point in time. And if the operating system has knowledge of the topology of the DRAM, it can choose a row in the same subarray as the one that the data is being copied from. And then you can use the fast parallel mode to copy. Bulk zeroing, again, you can use the fast parallel mode to copy data from the reserved 0 row as opposed to writing zeros. This is easier, of course. This is a bit harder. And then handling data reuse after zeroing. This is actually interesting. The paper does some analysis of this. There's some data reuse that happens after zero initialization. So in the phase 1, OS zeroes out the page, and then in phase 2, application uses cache lines of the page. RowClone is good because it avoids misses in phase 1, but it causes misses in phase 2. And the paper realizes that you don't want to cause misses in phase 2. What it does is it actually inserts clean zero cache lines to the cache. Whenever you're doing a zero initialization, you can insert clean zero cache lines into the cache also, while also updating the memory. That's the idea. And there's some performance analysis in the paper that shows that this performs better compared to both the baseline and RowClone without doing this. Okay, let me give you some more key results. I've given you the raw key results, now the system simulation results. The paper has some methodology for simulation. You can read about it in the paper. It's DDR3 and spec workloads for some cases, but also the paper uses some 6 copy and initialization intensive applications, because a lot of the spec workloads are not that intensive in terms of copy and initialization. And the paper uses some metrics, instruction throughput for single core and weighted speed up for multi-core. And these are the copy and initialization intensive applications the paper proposes. It's not from a single workload suite. The paper actually develops these itself, like system boot up, compilation, forking. The paper actually used a case study of this micro benchmark, because in forking you can vary the amount of memory that you're copying, right? It's good to do that case study to understand when this is very beneficial and when this is not so beneficial. But I'm not going to talk about that case study. And memcached, MySQL, shell. And the paper first analyzes the copy and initialization impact in these workloads. This is the fraction of memory traffic. Some of them are caused by writes and reads, but some of them is caused by zeroing and copying. You can see that in fork with some settings, a lot of it is caused by copying. In the shell script that is listing some directory structure, you see a lot of copying as well as a lot of initialization, and boot up has a mix. These phases of memcached and MySQL have some amount of zero. The takeaway, I think, is that the benefits correlate with the amount of zeroing and copying that's happening in the benchmark workloads in the baseline. So basically these are the benefits in terms of single core results. If you're running these on a single core, this is the performance improvement that you get in terms of RowClone. Now the paper somehow assumes that all of the copies are done within the subarray. This could later be a weakness also. That's the assumption in the paper. And in a sense it could be optimistic, right? But the benefits are significant if you could do that. The IPC improvement is significant, 40% in forking, 30%, I guess it's also 40% in shell. And memory energy reduction is even more significant, because you're really reducing a lot of the data moment, getting rid of all of the interconnect energy. And improvements correlate with fraction of memory traffic due to copy initialization, as I mentioned earlier. Multi-core systems benefit even more, basically, because you have more competition for bandwidth, because you have multiple cores competing for memory bandwidth. The paper does this case study type of studies where it runs copy and initialization intensive applications with memory intensive spec applications, and this could be a user scenario in real systems, right? In a cloud system you may be running an application that's doing copy and another application that needs to access memory at the same time. It may not be doing a copy, right? And this application may get delayed because the other application is doing a very big copy. And there's some methodology. You can read the methodology in the paper. And this is a summary of the multi-core results. You can see that the two-core, on average, the two-core performance improvement about 15%, and the performance improvement increases with increasing core count. And the paper also studies energy efficiency improvements. That is also reasonably high, more than 15%. So you get consistent improvement in energy per instruction. Okay. There's also more analysis in the paper that I'm not covering over here. It looks at fairness issues, for example. It shows that the fairness given to different applications improves, because now you're doing the copies inside the memory. You're not blocking the memory bus for a really long time. An application that needs to access memory is accessing it relatively fast because it's not blocked. As a result, overall fairness of the system improves significantly. I'm not showing it in these pictures over here, but there's a table in the paper that looks at many different metrics. So basically, this is the summary. Bulk data copy and utilization unnecessarily move data on the memory channel. They degrade system performance and energy efficiency. RowClone performs row copy in DRAM with low cost. It's a novel mechanism, and it uses a row buffer to copy a large quantity of data, and this is the fastest mechanism. It gives you significant energy and latency reductions. And this can accelerate copy on write and bulk zeroing. As you can see, there are many applications that can take advantage of it, and the paper shows that you can get significant performance and energy improvements in multiple types of core systems. These are some example results from 8 core systems, and the mechanisms come at low area cost. That's good. So this is my 25 minutes. How did I do? Not terribly. I guess we spent some time early on to set up the stage, right? So if you do a summary like this, it's not bad. Hopefully it's understandable, right? Okay. This is a simple idea. So it's simple to explain also. So okay, let's talk about the strengths of the paper. As I said, it's always good to start with the most important strengths. I think, and this is proven to be wrong still, yet it's a simple and novel mechanism to solve an important problem. It's effective and low hardware overhead. Intuitive idea, I think. I like these intuitive ideas in general. It's actually surprising that no one has done it before until 2013. There are some extremely weak patents in the area that don't give you any idea of how to do this, but there are some extremely weak patents that are referenced in the paper. It greatly improves performance and efficiency, assuming data is mapped nicely. That's a big assumption that's going to feed into weaknesses or potential limitations. It seems like a clear win, especially for data installation, because that doesn't have any mapping requirements, right? Because you're just writing zeros. You already map the data. You don't need to deal with source or destination pages. You just need to write zeros to a particular location. That's where it could get adopted immediately, I think. It makes software designers' life easier. The paper doesn't really talk about this, but imagine this if your copies are 10x or 100x cheaper. 10x in terms of latency and 100x in terms of energy. How do you design the software? This is where I have stories, actually. But for example, whenever you're doing virtual machine cloning in a single system or in a distributed system, you need to actually copy a lot of pages internally in a system. And if you want to do that, you actually don't want to do that. Let me put it that way. If you want to do that at low latency, you don't want to do that. So software designers in a company like VMware, for example, go through a lot of hoops to ensure that they minimize those copies. They don't want to do that. And they rewrite their software, and the software becomes a huge mess to read. If you're interested, you can read the zero-copy network stacks, for example. Zero-copy network stacks have the same problem, although I think virtual machines have the problem even worse. But as a result, the software becomes terrible, I think, both to maintain as well as read. So if copies are a lot cheaper, maybe the software doesn't need to become terrible, right? But it's a very different mindset. This is something that cannot be evaluated in a single paper easily, in my opinion, to show. And paper tackles many low-level and system-level issues, so it spans across the stack, basically. And I believe it's a well-written, insightful paper, but of course it's my paper, so I'm a little bit biased. I try to make all my papers well-written and insightful, and I think hopefully we succeed in almost all cases. Okay, now let's go to the weaknesses. This is where you really need to be critical. But I'm going to do this for you. You're going to do this for your own papers. So it's, again, important to start with the most important weakness. I think I tried to order these based on the most important ones. I think this is one of the big issues. This requires data to be mapped in the same subarray to deliver the largest benefits. How do you enable that? That requires, I think, system-level plumbing and changes. You need to change your memory allocator, you need to change your operating system. You could expose this to an application directly. A lot of GPU programmers actually can maybe used to things like this, but I think the visibility that you require over here is different from existing systems, because today no one is aware of the existence of subarrays in the system. That's the novelty of the paper. The paper actually exposes the subarray to the system designer if you want to get the biggest benefits. That information is not exposed. In DRAM, basically, the abstraction is that system knows about a bank, but nothing else underneath it. So that abstraction needs to be broken, and somehow interfaces need to be provided to communicate how data gets mapped inside a bank into different subarrays to be able to take advantage of this. So there needs to be some interface to communicate with DRAM to be able to do that. I believe there are a lot of other benefits that could be enabled if you expose this information to the system, but RowClone is one of the examples. Clearly, it helps less if data movement is not within a subarray, as we've seen, right? And it doesn't help if the data movement is across DRAM channels. This is actually a limitation. And the paper doesn't claim to solve that problem. This is a different problem. If you're moving data from one channel to another channel, or one machine to another machine, clearly this is not going to help you. This is helpful when you're moving data inside a single DRAM module, DRAM chip. Okay, the next one, inter-subarray copy is very inefficient. That's true, you need to go through some other bank. And the next question is, can you do better? We're going to talk about that basically. Later work built up on this to actually make that inter-subarray copy very efficient. So this is actually a very good example of their downsides. How do you actually solve those downsides with future research? And future research actually solved this problem. As I said, it causes many changes in the system stack, which is related to the data mapping problem. So sometimes it's not easy to order these weaknesses completely, right? For someone, this could be the biggest problem, right? If you're an operating system designer, especially if you're a conservative operating system designer, you may get very scared of this. If you're a very forward-looking operating system designer, you would love it. I think most operating system designers actually love this idea, except there needs to be a lot of plumbing across the stack so that this gets to the operating system level to take advantage of. Okay, so basically you need to have an end-to-end design that spans applications to circuits. And as a result, in general, software-hardware cooperative solutions might not always be easy to adopt. But again, this requires a mindset change. As we've discussed in the first seminar, a lot of the solutions we're having today are software-hardware cooperative, right? The Cerebras' wafer scale chip, the in-memory compute engines, non-volatile memory, they all require hardware-software cooperation. And this is just one example, one simple example. Cache coherence and data reuse cause real overheads, and this is absolutely true. They do cause real overheads, and they need to be handled somehow. If there are more efficient mechanisms of handling cache coherence, that would be good. If there are more efficient mechanisms of predicting which data should be reused and when to do this copy, when not to do this copy, when to use which mode of copy, that's also good. Okay, now these are actually more, if you think about this, these are more conceptual weaknesses in the paper, right? And it's always good to classify the conceptual weaknesses in the paper, separate the conceptual from the evaluation. Because evaluation can always go to a rat hole. You remember the rat holes from last time? You could always criticize workloads, metrics, performance results, configuration. Those are easy to criticize. Conceptual is usually harder to criticize. You need to think about the concept itself. And these are more important in the end because these things change over time, but conceptual things remain. They're more fundamental. So okay, let's go to this one over here. Evaluation is done solely in simulation. That's one weakness clearly. But there's a good reason for it because you cannot build a DRAM chip that does it. But we're going to get back to that later on at the end of this presentation. You could criticize pretty much any computer architecture paper this way, almost. Not all of them, but it's not easy to manufacture these chips, let alone DRAM chips. Evaluation doesn't consider multi-chip systems. That's also true. The paper never claims that it works for multi-chip systems, but evaluation could potentially consider it. Maybe the benefits are lower if you're doing copies all around. That is also true. But again, you cannot consider everything in a paper. That's my excuse for it, clearly. But you can clearly see that we can go into a lot of rat hole over here, right? Are these the best workloads to evaluate? That's also true. In fact, when we wrote this paper, one of the pushback that we got from the reviewers was, why don't you evaluate spec workloads? And the reason is they don't do a lot of these copies and initialization. It's usually the system level workloads that are really, really interesting. Actually, I wish we were able to evaluate a lot of the virtual machines. That was our limitation in terms of the infrastructure. Our infrastructure wasn't very good at simulating virtual machine-based workloads. I think the benefits could be higher in those cases. But this is definitely a question. Are these the best workloads to evaluate? Okay. So remember the rat holes, right? We could talk about this forever. We could brainstorm about where it could be beneficial, but let's not get into the rat hole discussion. Let's pick the useful discussions. Metrics, configuration. I didn't even go into the configuration over here. You could argue that this configuration, basically if you want to reject the paper, you could argue that configuration is not good. And you will definitely be correct because there is no single configuration in the world, right? Okay. So let's talk about thoughts and ideas, extensions and follow-up work. We're going to have a more discussion later on. That's why I want to continue this. Okay, can this be improved to do faster inter-subarray copy? This is what I mentioned as a limitation. And there's follow-up work, and if you can do it, I would recommend doing this in your presentations also, finding follow-up work that fixed potential problems with the papers. This is a work by another of my PhD students, Kevin Chang, who identified that this was a problem and he wanted to solve it, and this is part of his PhD thesis basically. It's called low-cost interlinked subarrays. Basically the idea is to interlink the subarrays with very small isolation transistors so that you can copy data across the subarrays within a bank. And he showed that there are multiple benefits to it. One of the biggest benefits is actually copying data, but you can also reduce latency and you can do caching across subarrays. Can this be extended to move data at smaller granularities? I think that would be nice. It comes at a cost usually, meaning smaller granularities in a single subarray. I think that would be actually very nice if it's possible. I don't see any easy way of doing it. Fundamentally, smaller granularity requires additional hardware, and once you go into changing the hardware in the subarray, you lose a lot of capacity. Can we have more efficient solutions to cache coherence? I think the jury is still out. There's a lot more work to be done in this area. How do you minimize overhead? Data reuse after copy initialization, how do you do that prediction? That's also, I think, very important. Can this idea be evaluated on a real system? If so, how? Again, you need to manufacture, but I'll give you another example soon. Can similar ideas and DRAM properties be used to perform computation on data? So can we not stop at just cloning data or initializing data? Can we do computation? And Vivek asked the same question, and later on, as part of his PhD thesis, building on his RowClone paper, he also published this paper, which is the AMBIT paper. It essentially enables bulk bitwise operations across different rows. You can do AND, OR, and NOT across different rows. In a similar mindset of RowClone. RowClone does 2 consecutive activates, and this AMBIT work shows that if you do concurrent activates to 3 rows, you essentially get a majority function, bitwise majority, which is can be rewritten as a bitwise OR, bitwise AND, and you add some circuit elements so that you can do the NOT as well. Now you have a fully functional system, Boolean complete system inside your DRAM, right? So you can see that by asking these critical questions, you can actually enable some really, really interesting research. Okay, so these are some of the papers that were enabled by this work. This is the fast bulk bitwise AND and OR AMBIT paper. There are actually some other papers. This work actually builds on RowClone as well as AMBIT a little bit to do the processing, do the operations inside phase change memory. So they showed that you could do these operations inside phase change memory. I think the evaluation of this is very interesting because they actually evaluate machine learning and graph processing applications and show that those applications get significant benefit from these ideas. And more recently, this is kind of answering the question, can this be done on real DRAM chips? This is a paper that I think, sometimes I think that I wish we had done it, but these folks showed that using the soft-MC infrastructure, they showed that you could get the effect of RowClone in real DRAM chips that they've tested by modifying the timing parameters. They basically get the effect of 2 consecutive activates by changing the timing parameters such that you almost get 2 consecutive activates, and they showed that you could really get row-to-row copying in a single subarray in real DRAM chips off the shelf without any modification to any hardware. You need to have the ability to change the timing parameters. That's what you need to do. Okay, so there's clearly follow-up work, and this is actually not presented yet, but the paper is online already. This is going to be presented in October in 2019. So that answers the question, is this feasible, right? So clearly follow-up work showed that it's feasible in real life. Okay, so takeaways, these are my takeaways. It's essentially a novel method to accelerate data copy initialization. It's simple and effective, hardware, software cooperative. I think of these as good things, but you could also criticize this part clearly. And there's good potential for work building on it to extend it. As we've discussed, there's some work, but there's also some work that probably remains to look at different granularities to make things more efficient and effective, and multiple works already built on the paper. I've discussed some of them, but there's a lot more. And I think I also like to think about it this way. It's easy to read and understand. That's not necessarily true for all papers you'll read in your life. Okay, and the next step is basically discussion. Okay, this is a place. Actually, I think we should have probably discussed earlier, but I wanted to give you an idea of the full presentation. In general, it's good for you to add discussion starters as well. For example, do you have any thoughts on previous ideas? How practical is this? Will the problem become bigger and more important over time? Will the solution become more important over time? These are some generic discussion starters, actually. You can use this for pretty much any paper, right? So if you don't have anything else, use these discussion starters to start a discussion. Are other solutions better? Of course, it's good to quantify some other solutions or qualify some other solutions. Is the solution clearly advantageous in some cases? I think zero initialization is one example where it's clearly advantageous. And given the compute DRAM paper that I mentioned, clearly existing DRAM chips have capability to perform RowClone with reasonable reliability. Okay, and that ends the paper. So maybe we should have some discussion. Any thoughts? I think now I presented the paper. Yes?
So yeah. For initialization, we looked at the zero insert where it puts it back into the cache. And at the beginning, we discussed cache thrashing. And now I wonder, for the copying, is there any analysis that it would also make sense to put it into the cache while copying? Exactly.
I think that's a very good question. There's not much analysis in this paper, but there's good reason that you may want to do that. If you can predict which parts of a page that you're going to use, for example, after you do the copy inside memory, you can transfer only those parts into the cache. I think that we didn't do it in the paper because that now straddles the boundary between prefetching as well. So there's a lot of work that you open up at that point. But I think that's a very good idea to look into. So it's essentially, how do you design a prefetcher that predicts which parts of a page would be useful after a copy? I like that. You could use any off-the-shelf prefetchers. There are some prefetchers that operate at the page granularity, but the paper doesn't talk about that.
Do you know of any that looked into that?
I don't know of any work that looked into that, but that doesn't mean that it's not out there. I haven't seen any prominent work that looked into that for sure. I know of work that looked into prefetching a lot. There's a lot of work, but not in combination with RowClone. Any other thoughts? We should discuss more. Or ideas. Or any other criticisms, anything I missed in terms of the strengths and weaknesses. Which is certainly possible. That's how science progresses, right? By poking and saying, oh, you missed this one, this is not covered, this is not covered, this is not covered. That's how really everything progresses. Yes?
Does the cache line initialization still use the bandwidth to memory control?
No, that's the good part about zero cache line initialization. You can directly initialize the cache line while doing the copy inside memory, because you know which cache lines you need to initialize, right? But the other one, if you actually want to figure out which parts of memory that you're going to use after a copy, there you will need to use the memory bandwidth. But zero initialization is very nice in that sense. Yes?
It's not a direct question for this paper, but I was just wondering, in, let's say, an SSD or similar, if you copy something from a location in an SSD directly to the SSD again, does it always go through the processor currently, or is there already like a shortcut in there?
So that's a great question. As far as I know, it goes through the processor, but the processor is on the SSD. Meaning that you don't go through the CPU that you're running tasks on, but there are dedicated processors that do the processing inside the SSD. So you still spend a lot of energy.
But at least not on the CPU.
Not on the CPU. Yeah, that's right. It would be terrible if you actually went to the CPU. A lot of the SSD storage tasks are offloaded by the CPU into the processor that's in the DRAM, not in the DRAM, in the SSD. But that's a very good point. Now you can think, can you actually do this on a flash drive, right? Can you do RowClone in flash memory? As far as I know, there's no work on that one, although it may not be that easy in flash cells. Is there any work in that area? Yes?
But on the flash idea, it might be a bad idea since flash has a very comparatively small lifespan. So we could use this as an attack to literally destroy part of the SSD, which would be a problem.
That's right, exactly. If you do it always in the flash memory, yeah, exactly.
Destroy some banks by will.
Yeah.
That would be great, I guess.
But if you're copying a file to another file, let's say, you're going to write to the disk anyway. You might as well do it inside the flash memory, right?
That's it.
Yeah. It's not clear if this is really increasing the raw number of writes to the SSD. If you're increasing the raw number of writes by doing this, yes. But that's good. I think I like the critical thinking. It's always good to criticize the idea whenever you see it. What else? Any more thoughts? Can you think of other solutions that could potentially be better? Not yet? If someone comes up with something better, I would be very happy. Because as far as I know, in DRAM, this is the, well, if without changing the array structure, this is the best you can do. You need to move the data into the row buffer somehow. Or maybe there's some other way, I don't know. Let's see what else. Well, okay, will the problem become bigger and more important over time? What do you guys think? Yeah?
As applications, especially data science or machine learning, are becoming even more data intensive, I think it will become more important.
Yeah?
Also, as memory grows, memory usage grows.
Yeah, exactly. I think that way also. Of course, this is more speculative, right? But clearly things are becoming more intensive. And there's a lot more data movement that's happening. I think the problem will become more important. I believe solution will become more important too. I think that's one of the reasons why the Google folks in their ISCA 2015 paper referenced this paper, saying this is a good potential solution to reduce the data movement overheads that we're seeing in the processors. Yes?
Can it be that, like, if we say, like, if we assume memory grows and gets bigger, that the solution of this paper also gets less efficient, because the data will be, if the chunks of data will be larger and more distributed, it will be less efficient, because we have less of those cases where we really are efficient and fast.
Maybe, but I think it depends on this data mapping part, right? How you map the data. If you design a system that can map your data, if you can localize, if you can maximize this intra-subarray copy or fast parallel mode, then it probably doesn't depend on the memory size. In fact, I think, although this is also speculative, right? If your chip size becomes larger and larger, now you're going to house more data inside the chip. The probability that you're going to go to some other chip reduces, some other module reduces. So this solution may become more effective. Of course, this is very speculative, because as your chip sizes become larger, the application data sets are also growing. The question is which one is growing faster, right? I think application data sets may be growing faster, frankly, depending on the application, because we can generate a lot more data than we can grow the size of our chips today. But that's a very good point, thinking about how chip size affects, how a DRAM chip size affects the solution effectiveness. That's one of the reasons I put the data mapping as very fundamental. That's the first thing that I said over here, right? Where? Not here. Oh, okay, I don't want to go back all the way over there, but that was one of the weaknesses. At least that's a weakness that the paper didn't solve. What else? These are good points. I like this sort of discussion, and I'd like to encourage the spirit of discussion during this seminar, because that's the way you can learn best, I think. Yes?
I was thinking about the security risks involved with this.
Okay.
Could it be possible for an application to block other applications from accessing the memory by copying data from one bank to another continuously? Okay,
that's a very good point, actually. Essentially security in the sense of denial of service type of security, right? Can this make it worse compared to a baseline system? Any thoughts? Yes?
Well, the memory control is quite fair, more or less, so if we don't design this to be fair, it would be a problem.
So I think what you're getting at is it depends on the memory controller you design, probably. So that's a problem in existing memory controllers also. If the existing memory controller copies data from one bank to another bank, it actually is a much longer latency than what the proposal is. And if you don't do it fairly, then you will run into bigger problems in existing systems. The paper basically reduces that latency. The memory controller does exactly the same thing, but just orchestrates the actions between two banks. So if the design is such that you provision for that, such that, for example, you don't do that byte by byte or 8 byte by 8 byte copy consecutively all the time, but you enable some other applications to access the bank in between, you can potentially reduce that risk. But I think the problem is much worse in the baseline system. By reducing the latency, this work reduces the probability of unfairness. But it doesn't eliminate it, clearly. What else? These are good points. You see what other questions? How practical is this? Any thoughts? Well, clearly somebody else demonstrated that it could be done on off-the-shelf DRAM chips, right? So at least we're not going to get that complaint anymore. Because it's amazing. Whenever you propose a new idea, you get all kinds of complaints. Some of them are correct, some of them are not correct in terms of, and practicality is always one of them. But it's always good if someone else reproduces your work and shows that it's doable. Yes?
The practicality really depends on the interface that the memory controller gives to the upper layer of the stack.
Mm-hmm.
Because if exposing these subarrays is just really tedious to program for them, well, maybe people won't do it because it's super tedious.
Yeah, exactly. So there are multiple notions of practicality. One is can it be implementable, which is what I answered. But yes, there is also can it be adopted relatively easily? And I agree with that. I think then you need to have an interface that is easy to use, and maybe you wrap around all of this in library functions that programmer doesn't need to deal with, right? And I think in the end, these are relatively easy to wrap around in library functions. It's essentially the job of the memory allocator, right? So somebody who's writing the memory allocator needs to be aware of the subarrays. But of course, if the interface is not exposed, they're not going to be aware of the subarrays. So it's absolutely right that cross-layer interface is necessary. What else? Have we answered all the questions here? Are other solutions better? I guess there's no answer to that yet. Clearly, the paper compares doing this in the memory controller with the DMA engine. So that's the state of the art. If there are some other solutions, maybe it should be compared to. You can imagine. I don't know of anything. Okay, let's see if I have anything else. No other thoughts? So I'll give you a very brief history. So this paper is actually, I think I've given you a lot of history actually while we discussed it, but there's some more history. This paper, when it was first written, it was rejected, like many other papers do, get rejected. It was submitted to ISCA in 2013. The reviews were actually relatively lukewarm. They were not really reject right out, as we will see in some other papers perhaps. They were basically saying, oh, it's a weak reject, basically. I'll give you one example review, since you may actually be exposed to some of these reviews. This is a review that says it should be rejected, weak rejected. Although the review is very positive, I think. The proposed technique is simple and elegant. It nicely exploits key circuit level characteristics of DRAM designs and minimizes the change necessary to commodity DRAM chips. The paper weaknesses, I'm concerned on the applicability of the technique and found the evaluation to be uncompelling in terms of motivating the work as well as quantifying the potential benefit. Details on how to efficiently manage the coherence between the cache hierarchy and DRAM to enable the proposed techniques are glossed over, but in my opinion are critical to the narrative. So maybe you can evaluate the review also. What do you think? Any thoughts? Clearly there's a strong positive. And this is not an unfair negative also, in my opinion. We've already discussed a lot of these. Given this, what should the verdict be? accept, reject, I don't care. This is the decision makers games that we discussed last time. Actually, I should have done this experiment in a different way. I should have given you this review and asked you if this was an accept or reject or don't care. What would you have said if you zero out all the information that I've given you so far? Yes?
If we focus on the weakness part that is discussed here, the last part of the sentence with the critical implies to me that it would reject this paper.
Okay. Yeah, I guess that's true. The critical part is probably the operative word over there. Yes?
I'd argue it'd be accepted because the weaknesses are mainly on practicality and implementation, which usually are solvable, while the solution is elegant and simple.
Okay, I like that perspective also. I think I agree with that in general. In general, I think there are different, as we discussed, there are different types of weaknesses and strengths. It's very hard to solve everything in a single paper. Yes?
Well, I would argue that cache hierarchy and DRAM is something which you should tackle in the paper because it's something which is not simply a practicality, it's also something from the theory part, right? So it would be quite critical if we do not simply do something and the cache stack simply falls down to our knees.
Yeah. So I think maybe to give you some context, the paper proposed a solution, but the reviewer doesn't like the solution, right? Basically, the reviewer wants something more in terms of the cache coherence, which I don't know what it is. But I think that's what also you're getting at, right? Those things can be solved by future work potentially. Basically, doing the coherence through the DMA engine is the state-of-the-art solution. Essentially, if you're doing this through the DMA engine, you would do that. You would flush the caches first, right, from those pages that you're copying. Yeah, so this is the decision makers games in the end. You need to go one way or other, or you need to do a cop-out, say, I don't care. So in general, I'm more positive about the ideas and the potential. I share the same viewpoint as your colleague over here. These are more on the practicality and motivation and also things that we don't necessarily know how to solve at this point. But the paper clearly proposes something new and elegant, according to the reviewer, or nice and elegant, according to the reviewer. I would land on the accept side if this were my review, but clearly it's not my review, right? Clearly there are weaknesses in the paper that need to be handled somehow, maybe by future work, but there's enough motivation to push it out because there's some contribution there. Okay. So that brings us to the conclusion slide. So what should we do next? Any thoughts? I don't think we have enough time for another review, unless you want me to rush through it. There are multiple options. We can continue discussing RowClone. If there are more ideas, I'd be happy to discuss. Or we can end early. Or we can start the next review and end in the middle. This is voting time. Who wants to continue discussing RowClone? Maybe that's the last option. Who wants to start the... Yeah, go ahead.
Question.
Yeah, then let's discuss.
Continue this review next week, or would we just start it but then never end it? If we were to start the second review.
Oh, I see. I think, I don't know the answer yet, but it would be weird to start it and continue it in the middle.
Okay.
Let me put it that way. Because we had a lot of good discussion here that ensured that we don't have time for the full review. We actually have only 36 minutes. And I want to take a break before we do the review, if you take that into account. But if you want me to continue, I'd be happy to. So who wants me to continue with the next review? Okay, some people, well, interesting. Who wants to end the class today? Don't be shy. Who wants to continue the RowClone discussion and maybe do some more brainstorming? If there's anything left there. Anybody? Who doesn't care? Okay, some people don't care. So if you want me to, I think the majority wants me to continue with the next review. So the question is, do you want to take a break? Yes. So, okay, let's take a 10-minute break. Let's be back at 4:35. And then I'll do a relatively quick review for the next one.